Now, we have covered in our discussion so far the brief review of gas kinetics and thermodynamics aspects. We have seen the conservation law of thermodynamics, that is the first law and the second law. And we have also seen that in comparison to the incompressible flow, what could be the change of the procedure in analyzing the situation in compressible flow design. Before moving further, now I would like to discuss some very important aspects so that the audience can understand better what we are going and heading towards to discuss. In that queue, we must understand some fundamental aspects, such as if we talk about that let's say my investigation is based on that I am willing to perform some investigation on aircraft model, and this aircraft model has to be investigated in the wind tunnel. What is the wind tunnel? The first and foremost, please understand what is a wind tunnel. A wind tunnel, a subsonic wind tunnel, looks like this shape. That is, a convergent portion is there, and from the convergent portion there is a constant area passage, and then there is a something like this diverging passage, and either this side at the upstream or at the downstream generally there is a blower which essentially rotates and it creates a suction effect, and then the flow takes place. This constant area passage is very much important, where we have to place the model. That is, this is called test section, and this converging portion is termed as convergent cone, and this is known as diffuser. This is a very simple schematic of a subsonic wind tunnel. Please understand, like computational fluid dynamics, in performing the experiment, wind tunnel by definition it is a simulation mechanism, that is the experimentally simulation of the models, so that you can perform the measurements and claim the data, maintaining the similarity of the parameters, similarity of the flow situations, so that you can claim the data for the actual prototype, that is for actual aircraft, the worldwide. Apart from the CFD, for all the models of the aircraft or spacecraft are being investigated in this kind of wind tunnels alone. That means wind tunnel is essentially an experimental simulation of actual prototype, and we use for the actual prototype the scaled down model maintaining the similarity. Similarity, as we discussed in our previous discussion, that similarity means it the model as well as prototype, they should be geometrically similar, kinematically similar, as well as dynamically similar. When you insert the similarity between the model as well as prototype, then this situation leads to some non-dimensional number. For compressible flow, we have spoken that we got that the Mach number, Reynolds number, the ratio of specific heat, and the Prandtl numbers are very much important. And we have also seen that whenever the flow takes place, since the boundary layer is always present, then it segregates, distinguishes between two regions over the surface. That is one condition that is outside the boundary layer, which is almost assumed as a potential region, and inside the boundary layer it is termed as viscous region. Because what is the boundary layer? The boundary layer is a thin zone where viscosity predominates or the viscous effects are seen. And we have seen that in the potential region, in the compressible flow, the Mach number is a only similarity parameter. However, in the viscous zone, due to if the temperature effects are also considered, and hence if the conduction phenomena is also taking place and then within the boundary layer convection is happening, then we have seen that the Mach number, Reynolds number, gamma, that is this ratio of specific heats, as well as Prandtl number, all 4 parameters are important. Now, doing this exercise, we just said that apart from geometric similarity, that is the ratio of length scale should be having a constant proportion between model and prototype. We also said the kinematic similarity. This is the point of discussion here. Kinematic similarity says that the flow pattern over the model as well as the prototype should be same. What does it mean? Please see, in the flow pattern, we see from our fluid mechanics background that the streamlines are having similar shape. That means in the visualization, how you capture, you want to see the visualization through smoke, through tufts, wools, incompressible flow design, that is when supersonic flows prevails. Then you see it through optical flow visualization, where other optical techniques like shadowgraphy, Sillerian and interferometry do come in, and as well as you perform for high subsonic as well as in supersonic, and that too further hypersonic flows, you perform oil flow visualization. What all these visualization ensures that the streamline patterns over the model as well as the prototype, they are similar in nature. That means in the flow pattern, that is a kinematic similarity, there are 3 essential concepts we must see that. One is telling that is the streamline, other is said straight line, and third one is path line. We all know all these 3 lines from our fluid mechanics background, but what we should see here, that when the flow pattern is over the, let us say in the flow analysis zone, I am drawing these kind of lines. This I am claiming that these are my streamlines. What is a streamline? A streamline is that imaginary line at which on the streamlines everywhere the velocity of the flow field is always tangential to these streamlines. These are imaginary in nature, that is they do not present, but we assume they are there. Other lines, if suppose this is the point of where we are observer is placed or we are observing, and if some fluid particles are moving from here, and let us say at various time instant, suppose at t equal to 0 we start observing, and at t equal to -1, t equal to -2 and t equal to -3 and so on, and at t equal to 1, t equal to 2 and t equal to 3, let us say seconds. You are seeing this thing. Then if the fluid particles which all those fluid particles from this point which are already moved, all those fluid particles which has already crossed these points, if we join these particles with a line, we call it a straight line. However, if only one particle which has crossed this point, if we want to follow and this particle is moving something like this, then this is called path line. That means by definition all those particles at various time instant earlier which are passed through a particular point, let us say P in the flow domain, if we connect all those particles with a line, that is called a straight line, and this is a real line. However, if only one particle is considered and we follow along with that particle and we trace the path, covered by that particular particle which is tagged, that is called path line. And the third one which we said just now, that any point in the flow field, if we draw the line, it is always tangential to the velocity or vice versa. That is at the streamline the velocity is always tangential. That means in an unsteady flow situation, please carefully listen this point, that in an unsteady flow situation, all these three lines, that is one particular particle path line, all those particles which are passed through that particular point in earlier time stands, let's say -1, -2, -3, they are straight line, and the streamlines are all different. However, when the flow is steady, then all these lines, that is streamline, straight lines and path lines, are all same. This is a very much important conclusion we have drawn here. Please note that even though the path line and straight lines are real in nature, but they do not give much information about the flow field. Only the streamline, which is an imaginary or a hypothetical line, is basically gives more information. That too, when the flow is steady, since all these lines merge with each other, therefore, whenever you perform any visualization experiments, then you are actually telling the streamlines which comes through merging of path line as well as straight line, and then only you are drawing those lines. Now here it gives another clue what we said, that a steady and unsteady case. What do you mean by a steady case? Any flow field which is not time dependent, that is, where properties variation with respect to time is not present, then we say steady case. So what does it mean? If the time is not present, that is, the flow situation is not, the properties are not changing with time, then it means if we are considering the property that, let's say, velocity of the flow field, it is not accelerating or decelerating? No. To answer this, we must understand that there is a relationship which we have studied in the fluid mechanics, that the relationship between the material derivative of any property is related with the local derivative with respect to time, as well as the gradient of this property. Now what happens? Please see here that this could be, suppose if this property which we are interested in, the flow speed, then dV by dt can be written as del V by del t in the vectorial notation, and then this can be written as del dot del, which is a del operator, and del V. That means del dot V, you can write that. In the Cartesian notation, here what we can essentially say, if V bar can be represented as Ui, Vj and Wk, where U, V and W in the Cartesian coordinate systems are the velocity components in three respective directions. That means if the flow field is steady, I can write down here that this term, which is a time dependent local phenomena, local derivative of time, is actually 0. And this term which you are having here, this essentially is called the spatial derivative of velocity. That means this is a local acceleration term, and this is coming from spatial derivative term. Therefore, even though the flow field which is steady, the local derivative term is 0, however, the total material derivative, this is called total or material derivative, is still not 0, because this fellow is still giving you, allowing you that you can increase or decrease the area along the flow. That means the flow can still be spatially dominated phenomena, and hence it can accelerate and decelerate. Therefore, In the steady case, it does not mean that you are not allowing the flow to be accelerated or decelerated. The time dependent change of the property you are ignoring. Now, earlier things, if we see that in the real fluid situation, as we already discussed, that the viscosity is present for the real fluid. However, to analyze or simplify the flow situation, the viscosity is always present. And we have seen from the Sutherland relations, particularly for the air, which is of interest because in the aerospace sciences, the aerospace vehicles fly in the atmosphere where the only air is present. In that situation, the viscosity of air is more important, and for that Sutherland formula is helping us in evaluating the viscosity at a particular temperature. We have already discussed this thing. Now, we move on, that we just said it, that we have to perform experiment in the wind tunnel. In any wind tunnel, if we want to see it, let us say again I am drawing the convergent cone and a constant area passage, that is a test section and a diffuser. When the model is that is mounted here through mounting mechanism, either vertical or the back side, so that it is not going to hinder the flow situation here, then our idea is that I have to say that this flow is one dimensional. Please note, all the naturally occurring flow are actually three dimensional flows. But to simplify the analysis, if we say, which we are going to see in this course, is one dimensional flow. So, how to ensure a three dimensional flow to be one dimensional? To have this thing, apart from mathematically, you can understand from very basic point of view. Let us say if this is an aircraft model, a top view of aircraft, where the vertical tail is here and a horizontal tails are here and the wings are here somewhere of the same aspect ratio. That means, let us say I am drawing like this, that both are similar. Now, the flow is coming like this in this direction, and I am seeing the top view of the aircraft model in the wind tunnel, and I have to ensure that the flow over the model is only varying, let us say, along the x axis, but it should not vary along the y axis or the perpendicular z axis. Please understand, to have this, to ensure this, at any particular location equidistant, which is equidistant from the midline where the aircraft is mounted. First of all, the aircraft should be mounted along the center line of the test section, that is at the equidistant point or location from all the axes. That will ensure that if the flow conditions, such as the flow is coming unidirectional as well as uniform approaching towards the aircraft model, then at equidistant point these properties are essentially same. That is, there is no variation of the flow properties as well as thermal properties, thermodynamic properties are not changing along the y as well as in z direction, and we are only allowing, and we are interested in seeing the changes only along the x axis. Then we say that we have brought down a three dimensional flow to one dimensional. And that's, with this background, let us begin our discussion in compressible flow about the steady one dimensional flow, that is the steady one dimensional compressible flow situation. We have seen that we are studying here the barotropic fluid. That means the density is a function of, density is a function of a pressure alone. In this situation, we are ignoring the temperature effect on the density. because that is a weak parameter for us. For all those changes with respect to the pressure, we defined the compressibility, and we said that a compressibility can be defined as, let's say, beta is defined as minus 1 by volume and then d volume by dp, that is a fractional change in the volume with respect to pressure, such that when you apply a compressive pressure, the change in volume, that is the volume shrinks, and hence we say this is a compressibility reflecting that you are applying the compressive forces. And from this point we said it that whenever the change in density is negligibly small or it is almost constant, we said that is nothing but your incompressible flow. However, when the density variation cannot be changed, that is it is the more than 5%, we said it is a compressible flow. Therefore, considering this fact in mind, the density is varying in the flow field from one point to another, we are going to cover what is the one dimensional compressible flow behaves. Please understand, the variation of density with respect to pressure has a very strong effect on the wave propagation. Waves means that any disturbance from, let's say, if these are the streamlines in a compressible flow and suddenly there is some obstacle present in this compressible flow, or if the flow is taking place in some passage which are having some abrupt change in area, that is from here suddenly the passage is diverging. That means the fluid which is coming, the compressible flow which is coming in this passage, the fluid elements need to adjust this sudden area change, that is either an obstacle is present or a sudden area change. In both cases, the fluid which is approaching, a compressible fluid which is approaching toward this obstacle, or here in this situation where the sudden area change is there, the fluid element need to adjust themselves. But who will ensure this? The nature has given a technique that whenever an obstacle is present or there is an abrupt area change, then from that location the acoustic signals is that the information passed upstream with the speed of sound. This information which is passed from here to upstream with the speed of sound A tells the upcoming fluid, upstream fluid here somewhere, that please make your adjustment now, since there is an obstacle or there is a sudden area change downstream side. That means this for information which is passing is not directly going just like a straight line. This information actually passes in the way of a front, which is known as, that is from the obstacle, this information to the fluid is passed in the form of a small wave which is called wave front, which is traveling at the speed of sound. That is what our purpose first is, to see this thing. Now here we go. For this to understand that how the waves passes and how the acoustic wave propagation take place in the compressible flow, the simplest example as we considered in the fluid mechanics, let us say we have a hypothetical piston cylinder assembly for a one dimensional wave propagation. Please note that though we are considering the simplified case of piston cylinder assembly, however, the result can be obtained if we take a cylindrical as well as a spherical case as well. Therefore, in the piston cylinder assembly, assume that this is the flow situation actually present, that a flow is happening because if this is a cylinder piston which is progressing toward with a very small velocity dV. And since a fluid medium, a compressible fluid medium is present here, and because of this piston and its velocity dV, the fluid is getting compressed such that a wave front with a speed A is traveling towards right side. In this situation, please understand, I have considered not V but dV, just to ensure that this phenomena is occurring very less at very less speed, so that the process should remain reversible. Under this situation, if I am observing outside from this and observing this piston cylinder situation, then what I am observing, that this wave front is traveling to the right side. However, the fluid medium here, where the wave is already passed, is compressed, wherever the fluid this side is still motionless. To analyze better, let us reverse the situation. That means I myself go and sit on this wave. If I will be on this wave and start observing the flow phenomena, because what I am interested, rather than a moving wave front, for simplified analysis, I should have a stationary wave, and across that stationary wave, let the fluid flows. This condition, as soon as it is reversed, is shown in the B. What it says, if the observer is directly, let us say myself, I am sitting directly on the wave, what I will realize it here, that the wave, the flow is traveling at the speed at A at the now my left hand side, and moving as soon as it comes down here, because the speed was dV of the piston speed, the relative speed will decrease up to A minus dV. However, the thermodynamic property, if we see that here, if the original fluid, if had the pressure, temperature and density. Here, let us say we are interested in pressure and density, and almost temperature is not varying here. Then what we feel, that where the wave is compressed, this fellow, that is in this zone, has the pressure P plus dV, that is a small increment is already took place, and likewise let us say a small increment in density is also took place. However, still my right hand side in the figure A is that the pressure P and rho is still here. Even though I reverse the observation situation, that is sitting on the wave, though the velocity at the both side changes, that is the incoming flow is now at A approaching towards wave, a stationary wave, whereas the downstream flow becomes, due to the relative speed of the wave as well as the piston, this becomes A minus dV. However, still the condition here of pressure, density is P and rho, and whereas it becomes here dP plus dP and rho plus d rho. Moreover, to analyze better, let us have a small control volume which is drawn here, showing the dotted line all over covering the wave. Now, in this situation, we will apply the conservation laws, and we will see that what information we obtain about the acoustic wave propagation. Please note, when let us say the area where that wave is traveling is covering at both the wall, so that if the cross sectional area of this piston is A, then from this side the mass flow rate which is approaching, we can say the mass flow rate, the mass flowing per unit time, is nothing but in the one dimensional the rate density multiplied by the area and multiplied by the velocity, because A into V from our fluid mechanics, we know that this is the volume flow rate. As soon as the volume flow rate is multiplied with the density, we obtain the mass flow rate. Keep in mind, let's say this is the equation number 1. Now, if we move ahead and we apply from, this is also, you can say this, we have applied the continuity or conservation of mass, because whatever the mass approaching from here is going the downstream side, and there is no mass we are losing. Now, if we move and apply the conservation of momentum principle on this control volume, what the information we receive? If we apply the momentum equation on both sides, what we observe that from the Newton's second law, we know that the linear change of momentum of the flow or any matter is equal to the applied force, that is F equal to ma. The same principle I am going to apply over here. The force which is changing in terms of pressure, please see that the downstream pressure is P plus dP, which is higher than P. Then how much pressure difference we have observed? P plus dP minus P, and when this pressure difference is multiplied by the cross-sectional area of the piston, this ensures how much force is acting while the fluid is flowing from upstream to downstream over this control volume, and which is coming through when how much linear momentum is changing from your upstream to downstream, which is nothing but, we can see it here that the mass flow rate times, you can see here the change in velocity. Please note that the downstream velocity, that is A minus dV, and upstream velocity is A. So, the change in velocity is actually A minus dV minus A, and when it is multiplied by m dot, then it gives you the change in momentum, that is dP by dt. And this is nothing but what you have done, m dot delta V. And this is equal to change of linear momentum is equal to applied force on the matter here, fluid, or the control volume is nothing but Newton's second law of motion. So, now if A is multiplied by P plus dP minus P, we obtain this. Simplify this equation and we get it something like dP is equal to rho A dV. Please look at carefully that this is nothing but your Euler's equation. Now, using your continuity which we have derived here, that again using the continuity equation, what we know that one dimensional continuity equation says under steady case that del dot V is equal to 0, that is the one dimensional continuity equation. Therefore, being that it is a vector, and if with this vector is having only one component, this can be brought down that del u by del x is equal to 0 under steady case. The same thing is applied over here, and this leads to you that the density multiplied by the velocity at the one end, that is the downstream, and is equal to upstream. And this continuity application, that is the downstream side rho plus d rho is my density and A minus dV is my velocity, which is the downstream flow is having, whereas the upstream flow, the density multiplied by the velocity. If you simplify and note that A remains unchanged. How this from apart from this, we can also note that what we have written here, rho A and capital A, we have written here, that is rho A V, that is here A is nothing but, this V is nothing but rho A, because the approaching fluid velocity is here A. Now, if I same mass flow rate without the mass, what is happening, then I can write down rho plus d rho and A minus dV, because the downstream velocity is this, however still the area is A, because the control volume both sides has the same area. If we equate this thing, we will obtain this, because A is cancelled out at the both sides. Then simplifying this thing, what we observe, that d rho by rho is nothing but dV by A. Let us say this is the B equation, and from the momentum term we have already obtained A. From A and B, what we are going to observe, sir, is a very important relation, something like A square dP by d rho. If you club A and B, then we obtain A square is nothing but dP by d rho. Now, speed of sound square is nothing but the derivative of pressure with respect to density, but still we have to make some arguments. We ensured that the piston, the hypothetical piston, is moving at very small speed, so that the flow is reversible, that the process is reversible. Furthermore, since sudden changes in the flow situation we are not allowing, therefore temperature effects are ignored. That means if we are considering the control volume across the wave, which is our main interest lies over there, for which continuity as well as momentum equation we have written, we have said it that the flow is reversible. Moreover, this control volume is not exchanging any heat from the surroundings. In this situation, the control volume can be termed as insulated, that is, its adiabatic process as well. So as soon as the process is reversible and adiabatic, we have seen in our previous discussion, we said it isentropic. Therefore, this equation which we have obtained from continuity and momentum by applying over the control volume, we can say that this is nothing but we can write down at the constant small s, that is nothing but at constant entropy. As soon as we get this thing, we go here, that let us say in the next slide which I have written for you is A square is equal to dP by d rho at constant s. That means this implies that A is equal to square root of dP by d rho at constant s. Now, this is a general speed of sound relation for any gas at constant entropy. If we are dealing the situation of ideal gas or a perfect gas, then we know that the perfect gas follows the thermal equation of a state, because what is a perfect gas? A perfect gas which follows the thermal equation of state as well as the calorical equation of state. We have already discussed and elaborated the things. Now, applying the same concept here, that since the pressure is following as this equation of state, the flow following P dP, P is equal to rho RT. Then differentiating with respect to rho here, immediately we get here that this is dP by d rho at equation. Using this, as well as since the process is isentropic, therefore the pressure and density is varying something like this, that is P by rho to the power gamma is equal to constant. If you differentiate using taking the logarithmic of this term and this term, you will lead to a equation which we have already used and shown it A is equal to square root gamma RT in our previous discussion. Let us see how it comes. Using this, the equation of state, and this relationship for isentropic case. Please note, I am dealing with the compressible flow situation. Therefore, applying the reversible and adiabatic case, I must have a P by rho to the power gamma relationship, which is nothing but which is valid relationship between pressure and gamma for a isentropic case, isentropic flow situation. In doing so, this exercise, if we take the logarithmic of both sides, we lead to ln P minus gamma ln rho is equal to ln of constant. Let us say this is a new constant. If this is termed as, for example, C1, let us say this becomes C2, which is nothing but ln of C1. Now, differentiating both sides, we know that logarithmic of any variable, if we differentiate, it leads to reverse of that variable. That means this becomes 1 by p minus gamma, 1 by p, that is dp by p, and minus gamma d rho by rho, which is taken right hand side, because dp by rho, the previous equation, dp by rho, dp by p minus gamma d rho by rho is equal to 0, and when we put this term right hand side, what we obtained here, that dp by d rho, taking this fellow down and p this side, we get this. Now, using the equation of state as we stated, we can directly write down gamma RT, and in the speed of sound, if we put dp by d rho in place of this, we immediately lead to this, and we say the speed of sound is something like this, where gamma specific heat ratio, R is a specific gas constant, and T is the temperature. This is a very important relation for a compressible flow or a gas dynamics. Please keep in mind this relationship, because again and again we will be using in analyzing the flow situation. Now, we move ahead further, which is very important. I am going to discuss, which you will enjoy about this concept. Many of you might be knowing, and many of you who are not knowing, please pay the attention, which we are going to see the interesting fact of this simplified relationship, which is easily obtained. We know that this is a specific gas constant, and specific gas constant we have seen from kinetic theory of gases that can be written as universal gas constant as divided by the molecular weight. That means if this is replaced here, what we see here, that A can be written as gamma Ru by mw T. Here I have written rather than R bar, which is nothing but my Ru, universal gas constant, and then this is nothing but your molecular weight. Please note that gamma, as I said in the previous discussion, gamma is a very narrow range parameter, that is between 1 to 1.67 for the polyatomic gases, because gamma is slightly more than that. However, it is less than or equal to 1.67, it means that it is 1.4 or 1.67 for monatomic gases, and 1.4 we have already seen that from the kinetic theory that this is for diatomic gases. And air is assumed because of oxygen and nitrogen percentage in the atmosphere, their percentage is more, and we say this is a diatomic gas. Since this is a narrow range parameter, it is not going to affect much in our discussion now here. Please see, since gamma is a constant and Ru, that is universal gas constant, is nothing but 8.314 joule per kg into Kelvin. In that situation, this is again a constant. Now, what is happening? If temperature is not varying, that is for a constant temperature case, the speed of sound is basically dependent upon the molecular weight, and they have the inversely relationship. So, what happens for the lower molecular weight gases, that is the lighter gases, have the speed of sound traveling in them is much more, whereas if the molecular weight of the gases is high, let us say oxygen, nitrogen or such cases even beyond, then the speed of sound, that is the acoustic wave signal propagation in those gases, will have lesser speed. This leads to a very interesting conclusions in terms of turbomachinery, which is a very much backbone apart from the ground facilities for aircraft. We do have a compressor over there just next to your intake for high speed planes like such as supersonic and hypersonic planes. This compressors and turbines, they have the blades. Now, what happens when the flow approaches to these the blades, due to the speed, these blades are rotors, or in terms of turbomachinery nomenclature, rotors and stators we know from propulsion background. And when the flow approaches these rotors, the stress considerations are major factor in designing these blades. However, apart from these considerations, stress consideration for normal speeds, when the situation is something like aerospace application as high speed case, here is an interesting fact. Generally, the speed range which is kept in turbo machinery is something like 270 to 450 meter per second, just to ensure that the design is fail safe for these rotors. However, from this discussion, what we note that the speed of sound, as I said, in lighter gases is higher. Suppose I am using hydrogen in this compressor, then the speed of sound is something like 1200 meter per second, 1200 meter per second. Whereas if I am using the heavier gases, let's say Freon 22 refrigeration gases, CCl2, F2, chlorofluorocarbon, then in that case the speed is something like around 110 meter per second. And normal speed of sound in the air under sea level conditions is something around 330 meter per second. Now please see, you are intelligent enough to understand this thing, that since we are keeping, just to ensure a fail safe design for rotors, we keep the speed of rotation something around 270 to 450 meter per second. That means if I am using the hydrogen as a gas and flowing over the rotors for turbo machinery for compression, so that I can get the compressed hydrogen for my further and flowing to the combustion chamber for propulsion, then the stress consideration are only the criteria and the flow speed, since for traveling the acoustic speed is 1200, this is not going to bother, because sonic consideration, because any flow traveling exactly equal to speed of sound, we say sonic speed. That means we know that is the Mach number is equal to V by A. If this is 1, that is the flow is moving at sonic speed, then V is equal to A. This also leads to the sonic consideration, that is the compressibility consideration. That means the design may fail even if we are not ensuring the fluid compressibility on the structure, that is the rotor. That means the fluid structure interaction plays a role there. If I am using the lighter gas such as hydrogen, it is not going to affect my design. Therefore, without botheration, you can go ahead if you are keeping the speed range is something in this range. Then only the stress considerations are important. However, if we are using the Freon, where the sonic speed we have just seen here 110 meter per second, then please note, if we are moving for your compression point of view for ensuring a particular compression ratio just before the combustion chamber, then this compressibility consideration for designing of the rotor is more important than the stress consideration. Whereas for the air which is having the 330 meter per second sonic speed which lies in this range, the both considerations are very much important. I hope you understood this point carefully. Now let us see what happens theoretically. As we said, the acoustic speed, that is the sound speed of sound, is given by dP by d rho at S. What happens when the flow is incompressible theoretically? Then this goes to 0. Therefore, the speed of sound is almost reaching very high value, something like infinity and tending towards infinity incompressible flow, the speed of sound. Now let us see that the fluid motion realm can be divided into three different three different sub classifications, something like acoustics, incompressible flow, compressible fluid flow. Acoustic, where these waves are traveling at a speed of sound, though the the flow velocity is insignificant to the speed of sound, but there are in this realm, that is in this zone where we talk about, that is this branch of science, is still the pressure and density changes are finite, and you cannot ignore that. Now, in our discussion, in an incompressible flow, the flow velocities are very small compared to the speed of sound, and the changes due to the change in pressure is quite negligible. That is, even though acoustic wave is traveling, it is not doing much changes, it is not incorporating much changes in pressure and density. Whereas in compressible flow, where the waves travel, whenever the waves travel in a compressible flow situation, then the pressure density changes are finite and should not be ignored, and we must include them in the analysis. Now, let us understand the physics behind what is happening when the acoustic wave, which we have just mathematically derived, what happens when the flow, something like which we have investigated, that the piston cylinder assembly, a piston is moving and the acoustic wave is traveling. Simplified case which we are taking here, that whatever the flow is coming and whatever the acoustic wave is coming and creating the disturbance, that is, this is also termed as pressure disturbance. Now, in this due to this pressure disturbance, since the property variations of pressure density is taking place, pressure and density taking place wherever this acoustic wave is passing, then this information must be brought to the downstream side. That means, if the wave is stationary, that if this effect is coming, then the upstream effect must be reaching to the downstream case, and that travels at the sonic speed, that is speed of sound. Therefore, this gives our clue that what happens when the speed of the object, that is the flow speed, is varying, and it is less than the speed of sound, more than the speed of sound, or equal to speed of sound. At this juncture, to clarify my situation, please understand that in compressible flow, on the theoretical basis, we say that the object, that is stationary, and fluid is flowing. This is just to simplify the case, that we know that actually in aerospace vehicles or any vehicle on the ground, automobiles even, but for, let us say, for aerospace example, aerospace sciences, the aircraft and spacecraft in the sensible atmosphere, when they flow, then actually the object is moving, the vehicle is moving, whereas the outside air is assumed to be stagnant. This is simulated in the ground facility like wind tunnel, and we say we mount the model whereas the flow is taking place. These two looks very different scenario, but please understand, we are not interested in absolute velocity of them. Rather, the relative velocity is more important. Therefore, if you travel with the vehicle speed in the stagnant air, the relative speed is same when you are having a stationary model, whereas the flow is flowing past over this model. That means, whatever the speed of the flow or the object we are mentioning, keep mentioning that they are essentially the relative speed, not the absolute speed we are interested in. That means, if the vehicle is moving or if the wave is moving, and for analyzing the situation, we make the wave stationary, whereas the flow is taking place, which eases our analysis, then it is similar to the case that when the object is moving, that is wave is moving, and actually in the stagnant fluid. And that's why we are telling, if this relative speed between the object and the flow, let us see what happens with respect to the speed of sound. So, the moving ahead, this thing, if the object relative speed, let us say speed of the speed V by A is something that the source which is stationary, but it is, let us say, it is a wave emitting source, that is, it is producing some sound. However, it is stationary at particular point. 0 is here location that a stationary source is present over here. But being a three-dimensional nature, this source is going to produce spherical signals in the form of which on a plain paper like this we are denoting, representing as a circle. Now at the 0th location, this wave is propagating spherically extending. It is termed that at any particular stand, these acoustic wave propagations are represented as the superposition of all those waves which are emitted previous to that instant. That is, if we are interested in time t equal to 0, then we need to superimpose all those waves, spherical waves which have been propagated from that source earlier to this time instant, which is denoted by -1, -2, -3 time instants. Now in this case, when the source is stationary, clearly from the common sense we can say that these spherical waves are symmetrical in nature. Whereas, and here is suppose the object is start moving towards left. In this situation, since still the wave will be spherical all along, it is moving, and in the two-dimensional paper on this we can say this is a circular, which is represented as circular. Now at time instant t equal to 0, this circle is represented. However, earlier this source was somewhere here and it has propagated this wave, whereas if we consider about time instant -2, this source was somewhere here and it has produced like this. Now since this object is also moving, though it is lesser than the speed of sound, is still a considerable magnitude. Therefore, these waves, spherical waves, wave fronts, which we call wave fronts, they are not symmetrical in nature. However, it has become unsymmetrical. Now when the wave is still the speed is increased, and now the next situation, suppose if this v is equal to a. In this situation, whenever the speed of the object, that is the source in our case, if is equal to the speed of sound, it becomes 1, then what happens at this age, all the wave fronts coalesce to each other, and if we see it here, then the quite unsymmetrical wave fronts on the right side we observe. And if we draw a tangent at all these points where they are coalescing to each other, then we observe this wave front as a planar wave front, and this is also termed as Mach cone. And from this Mach cone, this zone is termed as zone of silence, whereas this wave front, wherever the wave front, inside the wave front we say zone of action. And all this zone of silence, the information is still not passed of this source that this is moving, whereas zone of action is that zone where the information has been passed and the people or object can felt.